Good morning, everyone. My name is Rika, and today I am presenting my project titled Mini Generative Pre-trained Transformer, an end-to-end development of a generative transformer model with a web-based user interface. So, in this project, I focus on building a GPT model completely from scratch instead of relying on a pre-trained model. So the main idea was to understand how the generative AI work internally from tokenization and attention mechanism to training and text generation, and then deploy it in a real world application. So when coming to the introduction, this project is divided into two layers mainly. That is, the first is a research layer where I implement a GPT model from scratch using PyTorch, which has a casual multi-head self-attention, and tokenization is also done, and optimization using AdamW optimization technique. And the second is a production layer where I build an AI content detector using DistilBERT and deploy it is using Flask. So the key idea is a closed loop system where the GPT model generates the text and the detector analyze whether it is AI generated, and this creates a complete pipeline from the generation to the detection. So the GPT generates a synthetic text and the detector learns to catch it. So when coming to the technical stack, that is the tools and technologies I used here, this project uses a combination of deep learning and web technology for the user interface. So here the PyTorch is used to build and train the transformer model, and DistilBERT is used for the fast and efficient classification, and a tick token, that is a byte pair encoding technique which performs tokenization using subword units, and Flask API and Glassmorphism for user interface. Glassmorphism designs a better visualization, and the training was accelerated using the RTX 3050 hardware GPU. And this slide, I will be explaining how the attention works, which is a most important concept behind the GPT model. So, for example, the cat sat on the mat because it was tired. So, the model must figure out that it refers to the cat and it is not referring to the mat. So this is achieved using mainly three components, that is query, key, and value. So the query is what we are looking for, that is it here. And the key is what do I contain? That is what the each word contains. So cat, that is, we say it is an animal, and the value is what information is passed. So the cat sends its full meaning, that is the value. The model calculates similarity between the words and assigns the weight using the softmax function. So the each word designs how much attention to give to the other word. And this mechanism is what makes a transformer most powerful. And when coming to the GPT architecture, that is, it shows the process, that is the text by text steps. And first is the input text is tokenized into a smaller units, And these tokens are converted into embeddings or vectors in the byte pair encoding tokenization. And the positional embedding that is added so the model can understand the order, that is the positional info. And then the core part is the casual multi-head attention. That is, it ensures the model looks at the past token and it does not look at the future token. That is, it looks only at the previous word. And finally, the feed forward layer, which refines the understanding. That is, the model predicts the next token. And this is an auto-regressive model where the output is generated one token at a time. So here we are only using a decoder. It is a decoder only GPT. And there are 4 to 8 attention heads and it contains 4 to 6 layers and the embedding size is 128 to 56. And here I'm using AdamW optimizer. So here I'm using two data sets and this all will be explained in the next slide. So when coming to the data and training part, the model was trained on a tiny story dataset and a tiny Shakespeare dataset. So the tiny story dataset is a short, simple story, which is a dense, clean, and for fast learning. And the tiny Shakespeare is a simple character tokenizer. So I'm also using here byte pair encoding tokenization. That is what we discussed before. And the batch data loader, that is the batch data loader, creates batches with context window. And the forward pass predicts the next token. And the loss is calculated using cross entropy loss. That is, lower is better. And the AdamW optimizer is used here. It adjusts the weight intelligently. And here a weight decay helps to prevent the overfitting. So AdamW optimizer is much better than a regular Adam optimizer. And here the learning rate schedule used are cosine decay and linear wake up, which helps the cosine decay to gradually reduce the learning rate, and the warm up phase stabilizes the early training. And this helps to achieve a better convergence. So, when coming to the architectural design, so this explains the internal components of the model. That is the embedding that is converted into tokens, that is converted into vectors, and attention layer that captures the relationship between the words, and then the feed forward network that improves the representation, and residual connections that helps the gradient flow and it prevents the vanishing gradient. And these techniques are used in modern models like GPT-3 and GPT-4. So the goal here was to implement this component manually to deeply understand the architecture. So when coming to the next slide, that is explaining about the DistilBERT. Here, to detect the AI generated content, I used DistilBERT, which is a compressed version of BERT. That is, it is trained using knowledge distillation. And where a small model learns from a larger model. So the model is fine tuned, that is for binary classification. And here we can see that the trained on a label set where the human text has 0 as value and AI generated text has 1 as value. And the output is a probability score. So, for example, like as an AI language model, I can help you understand. So, this increases the probability that it is an AI generated text. As an AI and the language models are the trigger words detected here. Okay, when coming to the training result, the model shows a strong learning behavior that losses decreased from a 4.9 or somewhat 4.9 value to a 1.5. That is, the validation loss is stabilized here. And this indicates that the model has learned meaningful patterns and there is no severe overfitting happening. And this is the final validation loss and the training steps. And overall, we can understand that is a healthy convergence and there is no overfitting, no severe overfitting happened. So, this is the interactive web interface, which I built using the Glassmorphism, and it is having many features like a temperature slider that controls the creativity and an output length controller that is a generation length that is a user can adjust the output length up to 2000 characters and here the backend uses Flask, that is the input is sent to the model and the model generates the output and the output is displayed in real time. And this makes the project practical and more user friendly. So this is the interface I developed. And when coming to the result and discussion, in this project, I successfully built a transformer model from the scratch trained on a real data set. So here I also developed a web application using Flask API and Glassmorphism and also integrated generation and detection that is generated that is XAI feature. Explainable AI is integrated with detection and the future improvement can be scaling to a larger model, improving the explainability and deploying on cloud platforms. And overall, this project bridges the theoretical understanding with the real world AI implementation. I hope so. Thank you.